this promotion talk. And this Professor Huang is actually our alumni. He graduated in 2001, and he is also a classmate of Jack Chen. You know? And then after graduation, he spent 2 years in the army. Then went to US to study high energy physics. He graduated in 2009 from University of Wisconsin.
No, Stony Brook.
Oh, Stony Brook. And then spent a few years in the Princeton University. And today he's going to give a talk on this from S-matrix unitarity to fundamental laws of nature. Let's welcome Professor Huang.
Thank you. Thank you very much for the introduction, and thanks for everyone for coming. So this talk is mainly about some recent work that will be with these collaborators. Actually, it's 2 sets of work, so and which should be coming out sometime before April. So since this is a promotion talk, so let me just start my story at the year that I actually arrived at NTU, which is 2014. So in 2014, so there's these 2 interesting papers that appeared on Archive. Now, from the title, you'll see it'll look like these 2 papers has nothing to do with each other. One is talking about Ising model, solving conformal bootstrap and fixing certain operator dimensions for Ising model. Here, this is talking about causality constraints on gravitational scattering. Okay, so these are completely unrelated papers. But there's actually one theme that is really underlying these papers, and that's basically that what they're doing is they're doing a direct analysis of consistency requirement on physical observable. Here, this is correlation functions. Here, this is the 4-point scattering. And so this is they don't really discuss what is the underlying theory. They just impose consistency conditions. And just by doing this, they were able to get precise predictions as well as implications for any, so a broad statement about any underlying theory. They have a precise implication for them. So let me just go on these 2 points a little bit. So, for example, for the Ising model, what did they do? So they're talking about a conformal field theory. Conformal field theory means that you have some conformal symmetries. So they're saying that, okay, let's assume you have some conformal field theory with conformal symmetry. That tells you that your 4-point correlation function is fixed to this form, where this is a function of 2 variables, which is just conformal cross ratios. So this is conformal invariant. This is being fixed by conformal symmetry. Now, conformal symmetry also, of course, we all know conformal symmetry means you can just stretch and in different regimes that the theory should look the same. So that means this 4-point function can be also expressed in an OPE limit, where it's expressed in terms of this is just some function called conformal block, which actually was discussed in the previous promotion talk last year, and multiplied by some coefficient. Now the important point is that unitarity tells you that this coefficient has to be positive. Now this is a non-trivial constraint, especially when you're considering it, since you're a conformal theory, and that means you can expand in any way you want. Different ways of expanding must give you the same answer, no matter what. And so just by this information alone, they were able to carve out the space of consistent conformal theories, where this diagram is on the vertical axis. This is the dimension of the exchange operator, and here this is the dimension of the external operator. And they were able to carve out the space of these are the only possible conformal theories that exist. And they can show that the Ising model, 3D Ising model, is explicitly this point. And so, in other words, the dimension of the operator and the dimension of the external operator and the dimension of the lowest exchange operator is completely fixed just by imposing this symmetry and solving the consistency condition. So as you see, we didn't write down any Hamiltonian, we didn't write down any explicit computation. It was just imposing these symmetries. For the other paper, which is talking about gravitational coupling here, what did they consider? They consider, let's think about any general gravity theory, where you have the Einstein-Hilbert term. Let's say you modify it by an explicit operator, R squared, with some parameter lambda. This is a Gauss-Bonnet term. Okay? then again, what unitarity tells you is that because this modification will modify your 3-point vertex, that means if you consider any two-to-two graviton exchange, this process will be modified by a phase factor. So this delta V, which I'll explain shortly, is going to be modified by this extra term. Now, what is this delta V? This is the time delay. So remember, when we're talking about gravitation object, right? When the light is passing through the gravitation object, it's going to be bent. So that means there's a certain time delay by this bending. And the classical Einstein-Hilbert is just this term, and the time delay is positive. That means that the light will be bent. But because of this correction term, here now you have this extra term here. And notice that this term you can, if you play around with the variables, you can easily make this term negative and bigger than 1. In other words, the time delay can be time advance just by putting in this correction. So what does it mean? This means that even though you can modify your action, and this seems like a perfectly fine modification, this actually causes non-trivial physics effect and cause violation of causality. So this tells us that causality is violated if this operator is present and if the gravity is weakly coupled. And they were able to show that this effect can only be cured by the presence of infinite number of new particles with spins bigger than 2. Okay, so this is very important because they were just looking at a simple effect, and which the consequence is fixed by unitarity. And they were able to derive these very non-trivial results, as well as implications for any underlying theory thereof.
That's why NIMA. I know that NIMA is proposing this heavy bosons of higher spins. I think this has something to do with that.
Yes. Basically, that's the other program which I've also talked about a few times before about the possible perturbative gravity completion, which must involve infinite higher spin massive particles. So this is also related. So there's actually multiple reasons that you need infinite higher spin particles.
Well, this is due to the R square term.
Yeah, this is due to the present switch.
So why don't they just give up that?
Yeah, sure, that's perfect. But remember that a lot of the FR gravity, a lot of the cosmology models, they will have like this kind of term appear in your effective correction for. And actually or put another way, any UV corrections to gravity will in general generate this kind of term, because that's just the first leading higher dimension operator you can put down.
Because if you don't have that, then you don't have this problem, right?
Well, if you this is just a leading term. You can also have R cube. R cube will also have this problem. So in other words, any possible way of modifying your 3-point vertex, either by R square or R cube, they will all have this problem. So that's the same.
When you mentioned R squared, square of the scalar curvature or R mu square?
It's the Gauss-Bonnet term. Yeah, it's not just the, yeah. So the moral of these two stories is that unitarity constraint on physical observable yield important model-independent results. Now, of course, this is nothing new. We all know about this. There's long stories of examples of this which we know and which are all in the quantum field theory textbook. For example, we know that exactly the same argument, if you consider the WW to WW2 scattering in the longitudinal modes. We know that the longitudinal modes grows polynomial, and that means that unitarity itself also tells you that you need new physics coming in, whether it's Higgs or something else, but it has to come in below 1.2 TeV, depending on how what kind of process you look at. And so this is a well-known example where unitarity was applied and implied non-trivial consequences of the physics. And even our usual notion of RG flow, right? When you think about RG flow, you think about we have some theory, and then along the RG flow, we lose degrees of freedom, and then and we get into infrared. And we will somehow have this notion that you're losing degrees of freedom, and therefore your RG flow is irreversible. Now it turns out that this notion by itself, we are actually implying unitarity, right? Because if you're saying that along the RG flow you're losing degrees of freedom, you're assuming a definite positive Hilbert space, which is only true when the theory is unitary. All right, so again, unitarity is basically the explanation for why RG flows are irreversible. And in fact, what we currently know about irreversibility of RG flow indeed just comes from the proof of unitarity. So so this is just a short line of how the 4-dimension unitarity, the irreversibility of RG flow was proven. So basically you can think about RG flow as a simple example between a UVC fixed point and an IR fixed point. And in IR, in the infrared, you would have a fixed point, but because you're breaking the UV-CFT flowing down, so that means you'll have some ghostal modes, and the ghostal modes are encoded in this ghostal mode effective action, where there's a parameter which encodes the conformal anomaly, and this parameter will appear here in your effective action. And it's basically just the optical theorem. You can consider the 4 boson particle interaction, and this parameter here, this delta A here, will appear in a particular 4 limit term. And this delta A you can show just by relating it as a contour integral, and using the optical theorem to relate it to a cross section to show that this is positive. In other words, the irreversibility, again, the reversibility of RG flow is just the optical theorem. It's again just unitarity. So this is nothing new. We've known a lot of examples where unitarity tells us non-trivial information of really the underlying theory and really why the physics law look the way that it looks now. So what is new about these 2 papers? So what is new is that, first of all, you have to identify the right physical observable. You have to identify the right objects that you want to impose your constraints. And in one case it was the S matrix, and the other case it was the correlation function. But more importantly, you want to have a convenient basis for the observable to impose these constraints. So it was very important, for example, in the correlation function discussion where they were able to prove the dimension of the operators for particular values, the existence of conformal blocks, which was actually, again, was talked about last year in Henry's talk. And so the existence of the basis is very important. So in this talk, I will follow similar spirit. So first I will introduce a new representation for massive S matrix, and I will identify the salient features of this S matrix to answer 2 questions. First, why are the fundamental particles in our nature that we actually observe are so limited? In other words, we all know that, well, of course we have the standard model, we have these particles, but essentially what you have is spin 1/2 and spin 1, and that's it. Right? Now we have a spin 0, which might be a fundamental particle, but essentially that's it. We just have spin 1/2 and spin 1. So I want to ask the question, why? I mean, what is really the underlying reason why only these particles are seen? Of course, we know that there's bound states, but we generally believe that anything beyond spin 1 is always a bound state. You cannot have fundamental particles beyond spin 1. And I want to answer the question why.
Graviton.
Yeah, graviton, but so graviton will be beyond spin 2, but I'll make that statement clear. So this is the first question I want to answer. And second question is, do we have a general way of understanding what is so a lot of the discussion we have is really about why the particles that we observe have mass much smaller than the fundamental scale, which is Planck. So is there a systematic way where we can understand why or if you're assuming that you're assuming a broad class of mechanism that guarantees that the mass is smaller than Planck, can we systematically pick apart the precise nature of that mechanism? So this is the 2 questions that I'll seek to answer using this approach. So the first is, again, essentially, this is not the title of the paper, but essentially what it's saying is that we have a new spinor helicity formula for massive S matrix. So this is work with Arkani Hamed and also with Huang, which was an undergrad student with me and now a grad student at Caltech. So to discuss spinor helicity, let me just remind you about massless spinor helicities, which some of you might have heard before. So massless spinor helicity is basically trying to solve the on-shell constraint using unconstrained variable. So if we have an on-shell constraint p squared equals 0, a massless momenta, we know that we can take a momenta and write it into a 2x2 matrix. So you can dot it into identity and the Pauli matrix. You have this nice 2x2 matrix. And p squared equals 0 is just saying that this 2x2 matrix is a rank 1 matrix. And that means that you can just parameterize your momentum just by spinor, because it's a rank 1 matrix, so you can write it as a vector. And the important thing here is that you solve this constraint covariantly, so you didn't break Lorentz invariance. So this is not like the usual light cone, where when you're solving Lorentz non-shell condition, you actually give up Lorentz invariance. No, this still preserves the Lorentz invariance. And actually, just to give you an idea of how powerful using these variables are, so this is the computation in 1985 where they just consider the 6 gluon interaction. This was a 30 30-page paper. And this actually does not contain the full calculation because, as you see at the end of the paper, the details of the calculation after 30 pages is going to be in another paper. But furthermore, they hope to obtain a simple analytic form for the answer. This is just a 6-gluon answer. And it's amusing that, but also a theorist delight. And a couple of months later, using these variables, they found the endpoint answer, arbitrary point. So for 2 helicity gluons and all positive gluons, this is the form. Very simple. This paper was only half a page in PRL once they found this representation. So you really using these kind of variables to express your final answer makes things extremely simple. And the event of the massive spinor helicity, of course, brought in a new era of computation. So people were able to develop new calculation methods, both at tree and loop level, and apply it to QCD and gravity, because these are masses. And because they're using these structures, as you can see in the previous, multi-gluon scattering is just a simple answer. That means that there must be a lot of hidden structures in it. And indeed, people have found a lot of hidden symmetries, dual-conformal symmetries. They've found new string theories that are defined using these and scattering equations, etc., new ways of deriving scattering. Which some of you might have heard of. But really, in all of this discussion, the elephant in the room was that whenever people start talking about amplitudes, we have these twisters, we have these very nice form of amplitudes. Every time we would just ask one question, but the real world is massive, right? Actually, the mass is the real definition for the S matrix. The real external states are really massive external states, not masses. What can you tell me about massive case? And this was always the problem with this whole massive spinor helicity formalism. And so we believe that now we have the correct way. We believe we have found the correct way to really look at what is the proper way to look at an S matrix properly, which is defined for massive particles. And what would you? Let's say if you wanted to find something like this, and what would you look for? Well, the simplicity of spinor helicity was really built on 2 properties. First, it solves the on-shell constraints using unconstrained variables, and then it manifests the little group covariance. And the little group covariance was the U1, and where these variables transform covariantly. So let's consider the S matrix and let's try to translate our external states into the massive little group representation, which is just simple SU2. Everybody learned about SU2 in quantum mechanics. So for example, what do I mean by we can just convert it into SU2. So let's say you have some massive vector coming in. So this is a massive vector. I can convert it into 2-component spinor notation, which is that 2x2 matrix that I introduced before. Now, I'm going to convert one of these index into the same SU2 as the other index. The way I do that is I contract it with the momentum of itself divided by the mass. Now, in general, this is like a 2-component tensor, but the statement is that this 2-component tensor has to be symmetric. The reason is because the antisymmetric piece of this thing is actually just proportional to epsilon dot p, which we know is 0. The on-shell constraint for massive particle, massive vector, is that it must be longitudinal. So the antisymmetric piece of this tensor is 0. So this tensor only has a symmetric piece, okay, for your external state. In other words, you can just parameterize your external states using always SU2 symmetric tensors. And what's the easiest way to build SU2 symmetric tensor? You just write something that is a product of two spinors, okay? So the proposal is, instead of always thinking about a scattering process as some wave function with some helicity, with some tensors, so these are higher spin particles. You can also think about Dirac spinors. Instead of thinking it in this form, you think about a new S matrix, which is expanded in these chi variables. Okay, and once you do this, you already achieve that you automatically solve the on-shell constraint. So that means my scattering amplitude, the probability of the scattering process, in the usual textbook where you write it as a polarization tensor multiplied with some momentum. Instead, now you write it as some auxiliary variable which you expand upon. So you expand upon these chi variables, and then here, really the kinematic or the dynamic is encoded in this function here, which carries these SU2 massive little group index. So now all we have to do is to try to write down what does this function look like. So there must be some function, and we need to find some building blocks to carry these free SU2 indices. So this is the idea, so we're going to, instead of thinking about Lorentz vectors, spinors, and so on and so forth, we're just going to think about SU2 representations, which is the simplest representation we
I
have.
thought you were relying on twister formalism.
No,
You're not.
no. So that I'm doing massive now. So I'm really.
So this chi alpha, they should be constrained in
No,
some
they're
way?
completely unconstrained. The reason that I introduced is just because that all of your polarization tensors are just symmetric tensors, and if you write it as chi, then automatically it's symmetric. This is just solving that it's a symmetric.
You don't have a traceless condition.
No, there's no traceless condition. This is just SU2 error.
Still, you're supposed to apply to the dimension 4.
Dimension 4?
Dimension is.
Yeah, this is dimension, because I'm using SU2, so this is 4 dimension, but this is where our world is, so I shouldn't apologize for being in 4 dimensions. Good. So let's just to show you how powerful just thinking in terms of this way is. So let's just consider all the possible 3-point interactions. So let's consider two massless particle and a massive particle for arbitrary states. So the massless particle are carried helicity weights, and the massive particle is just some SU2 error. Now, so we need something to carry these SU2 index, and it turns out, and this is a 2-dimension space because this is, SU2. So we already naturally have 2 spinors, the lambda 1 and lambda 2, of these 2 masses there to carry this SU2. And so if you write it in this basis, once I tell you what my helicity weight is and what spin it is, there's only one unique answer. Okay, so just by looking at this, you can see that 2 massless particle to 1 massive particle, there's always one unique answer. There's nothing else you can write down. Okay, and this is just a kinematic statement. So once I specify H1, H2, and spin, this is my unique answer. And this has very important consequences. For example, the well-known Yang's theorem is just a simple analysis of this, because if you set L equals 1, this object here is antisymmetric, and because it's a Bose particle, it tells you a massive particle cannot decay into 2 masses. This is just a famous, and it just comes out naturally here. So we can move on. We can consider 1 massless particle and 2 massive particle. Again, the massive particles are always labeled by their SU2 irreps, and the massless particle is by its spin. Now the SU2 index is carried by these 2 convenient bases. The lambda 3 is the lambda of the massless particle, and dotted into P2. At each step of the way, it's always the same thing. When we consider a new process, we just find what is the convenient basis to represent the SU2, and then you apply helicity weight and spin. And for example, in this case, you have various different possible tensor structures for the fundamental interaction. Now this is for the case where it's unequal mass, when these 2 particles are not equal mass. What we're more interested in the case where they're equal mass, because this would be minimal coupling. This would be a particle that is charged. I describe, for example, a particle that is charged, or a particle that is minimal coupled to graviton. So if it's equal mass, then you have a special constraint, which is because then you can see that P3.P2 and P3.P1 is 0, where P3 is the massless leg. And then this tells you that the lambda 3 is proportional to lambda tilde 3. And basically, I just want to say this is a special kinematics, and this special kinematics, you can define this special parameter here, x. And then your amplitude is just expressed in terms of x, your lambdas, and your epsilon, and it's also uniquely determined. And what is interesting is that if you consider a positive helicity, anything that is positive helicity, this expansion starts with something that carries no lambda and with extra term. And this leading piece here is precisely your minimal coupling. This is the minimal coupling. This doesn't look anything like what we see in quantum field theory book, but if you're interested, you can just go back. You take a massive particle coupled to a photon, a fermion to a photon, a WW to a photon, and this is how the amplitude looks like in field theory textbook. This is how it looks like. This is how it looks like, a very complicated form. But after applying our observable our variables in, it's just mass times x, mass times x, and mass times x, just with some extra Levi-Civita tensor. So it's extremely simple. If you just use our variable, all of these computations becomes extremely simple, and we'll see the consequence. We'll do some more examples later. And here, for example, you can immediately see what the magnetic moment is, because again, I'm telling you that the minimal coupling is just x times some times the Levi beta tensor. So once I convert it back into the usual form that we're used to, you immediately see that you have the usual electric piece and the magnetic moment piece. So you automatically get the G equals 2 here. And in a few slides earlier, we're going to see that the one loop correction to this is just now 2 lines using these variables. But of course, we can also consider all 3 that are massive particles. And again, we just now the SU2 is just represented, carried by these 2 operators. One is just the Levi-Chavita tensor. These are just the inner product of 2 momentum. So basically, we have a nice complete way of representing all possible 3-point interactions in a very clean fashion. So what can we do? Well, so first of all, we see that we have a complete basis, and this is really it's really settled by just kinematic statement. This is basically just asking how 3 particles can merge together. And this and by assuming that you have Lorentz invariance, this also already gives you a strong constraint for what the final answer is. But now we would like to ask dynamical question, which is, and the dynamics is going to be determined by unitarity. So what do I mean by unitarity in this context? For example, you can consider, let's just consider 4 particles scattering. And then this will be a function of 2 kinematic invariants in S and in T. So if I think about this function, this answer, as a complex function in S, that means there can be only 2 kinds of analytic structures. And these analytic structures must be on the real S axis. And one is a pole, and the other is a branch cut. The branch cut is, of course, we all know that it's 2 particle production, and the pole is just a single particle production. But here, what unitarity means is that on these poles and the branch cut, the residue or the discontinuity always have to factorize into the lower point. Now, in the previous part of my talk, we already constructed what all the possible lower point amplitude could be. So now unitarity then tells us what the 4-point particle should be. And there's actually a non-trivial constraint here. Why? Well, first, so let me just say it in words. Let's say if you take 3 particles and you glue it together. Once you glue it together, if the answer that you get still contains poles, that means that gluing in one channel is putting constraint on what the other channel can be. Okay, so then this becomes a global consistency condition. So, and this will have important implications. For example, let's go back to the massless case. So let's say if we learn very few field theory, and we say, oh, why cannot there be any self-interacting higher spin massless particles? Why isn't there? Why, if I look through the quantum field theory book, why isn't any discussion about massless higher spin? So we can think. Okay, let's say if there were such a case, then what would the S matrix of this thing look like? So of course, the 3-point S matrix is always fixed, just by similar analysis I did before. So it's fixed. So let's consider 2 minus helicity and 2 plus helicity with arbitrary spin. So this might be L. So this is a self-interacting higher spin. So we're gluing 2 3-point S matrix together. So you glue it together, and just doing some algebra, you can rewrite it in this form with a 1 over T. So this is what I said before. You glue the 3-point amplitude in the S channel, but your residue contains a T channel pole. This T channel pole has to make sense, and that's the consistency requirement. For example, if your massless particle is spin 1, then, well, that's fine. You have a T channel pole. That just tells you that your answer has both S channel and T channel, so this is your final answer. The S channel residue contains a T channel pole. That's fine. Okay, let's say you have spin 2, L equals 2. What does that mean? Well, now you have a double pole, which does not make any sense in terms of factorization. But we know that since these massless level, these 3 kinematics, U plus S plus T equals 0, that means since we're sitting on an S equals 0, that means U equals to minus T. So this T square pole is actually secretly a U and T pole. So that's still fine. And this is your gravity answer. But as you see, once you go L equals to 3 and beyond, you have this T channel pole becomes too high a power. And there's no consistency interpretation of that. And that's why higher spin particles beyond spin 2 cannot be consistently self-interacting. Okay. Now you might say, okay, there's no self-consistent interaction of higher spin particles, but maybe there's free particles, right? There might be higher spin particles that are just free. They don't self-interact. Am I safe? Right? Because you can assume, let's say you have spin